All right, today, class, we're going to talk about domain and range. Now, before we talk about domain and range, though, I want to talk to you about interval notation because interval notation is going to be the notation that we use to express our domain and range. So interval notation is used in algebra to show a range of values. And don't get this idea between range confused with this idea for range, right? When we talk about a range of values, we just mean from one place to another. So from like 5 to 10 or something like that. It looks similar to an ordered pair, but instead of x comma y, we always write it as the lower value comma upper value. And we'll use two different types of parentheses. So we'll use a parentheses when we can get close to a number but never quite touch it. We call that exclusive. Or we use brackets when we actually touch a number that's inclusive. Parentheses are always around infinity since we can never actually reach this number, thus it is exclusive. So if we look at these two examples here, the number of teams that are remaining in the NCAA basketball tournament at any time would be between 1 and 68 teams. Notice I put brackets around this because we can actually get to one team, right? It's not like we can get close to one team and then we're done. No. Once the tournament's over, hey, there's only one team remaining, so we can put a bracket around it. And before the tournament ever starts, there's 68 teams, so we do put a bracket around that instead of a parentheses. If we look at this next example, the possible values in a savings account that's never had a withdrawal would be between $0 inclusive and infinity. So there is no theoretical upper limit to how much money you can put in a savings account. You can keep putting money in forever and keep gaining interest on that forever. The lower value would be 0 inclusive because a lot of savings accounts, you don't actually have to have an upfront deposit to make them. Now, some notes on domain and range, now that we're okay with how we're going to write domain and range. Domain of a function is just all the possible x values that work in the function. So if we were to graph like the line y equals x, we see here that the domain would be from negative infinity to positive infinity. That graph extends in both directions, to the left and to the right. So since it goes forever to the left and forever to the right, yeah, I know it goes up and down too, but domain, we're just looking at the x values. So it's going forever to the left and forever to the right, so that's negative infinity to infinity. The domain for any polynomial function and several others is all real numbers since there's no constraints on them. So for this function here, the linear function, there's no constraints for what we can put in for x. We can put in any number. So another way to write negative infinity to infinity would just be to say all real numbers. The range of a function here is all the possible y values. So by range, write y for the y values there, right? Now, again, if we look at our linear function, we know it does something just kind of like this. And then we look at the up and down. And it goes up forever, and it goes down forever. And since it goes up forever and down forever, we look at negative infinity to positive infinity for that. Let's go ahead and fill out the rest of this table. The absolute value graph, we know it does something like this. So it goes to the left forever and the right forever. So again, that's all real numbers or negative infinity to infinity. But for our parent function, note that the range stops. It stops down here, and this would be at the origin or at 0. So the lowest y value we could get would be 0. And I'm going to put a bracket around that because we can actually have 0 for a y value. That works. And then the upper limit, it just keeps going up forever. So it will go up to infinity. The quadratic is going to be kind of similar to our absolute value. The domain, again, is all real numbers, negative infinity to infinity. But the range, we know that that has a minimum value down there at 0. So it goes up forever, but it stops down here at 0. So the range would be from 0 to infinity. For the cubic function, that's that funny vertical S-looking graph. And it goes to the left forever and to the y forever. Again, it's a polynomial function. There's no limit to what we can or can't put in for x. We could put in any value there and that would work. And then for the range, if we look at the ends of that range there, we see it going up forever to the right and down forever to the left. So that would just be negative infinity to positive infinity. The square root's a little bit different. The square root actually starts at 0, 0. Okay? Now, the reason for that is we can't put any negative values under a square root and get a real number for our result. So that would just be from 0. And then we can put any number bigger than or equal to 0 in there. So we could write that from 0 to infinity on the domain. And then the range is very similar. If we look at the range on this thing, it's going to start at 0, 0, and it's going to go up forever. Now the rate at which it goes up changes. It actually goes down, but it does keep going up. So it starts at 0 and it goes up forever. It just takes it a long time to get to infinity. Cube root looks kind of similar to our square root, but we see on the cube root graph that we do have this going forever to the left and to the right. So on the x-axis, that would be all the numbers down to negative infinity and all the values up to positive infinity, since that's going forever to the right. Again, the range is kind of funny because it does not grow very fast, but this does continue to go up. It never comes back down. And then on the left side, it always goes down. It doesn't come back up. So that means that this would eventually get to negative infinity. And on the right side of the graph, this is going to go up forever to positive infinity for our range. So that's a funny looking infinity. All right. And if I haven't mentioned it, yes, this little sideways looking 8 that I'm drawing, that's our infinity sign. The exponential function is the outlier of the group, I would say. So we know on the left side we have an asymptote at 0. That means it gets really close to 0 down here on the y-axis. But there's nothing that limits what we can put in for x. And since there's nothing that limits what we can put in for x, it's negative infinity to positive infinity. And then again, if we look at a quick sketch of this, on the y side, it gets really close to 0, but it never quite touches 0. What's happening here is as we move to the left in this function, we're taking half of the value each time. So if you take half of a half, you get a fourth. Half of that, you get an eighth. Half of that, you get a 16th. Half of that, you get a 32nd. And so you can keep making a smaller and smaller fraction until you get really, really close to 0, but you can never quite touch 0. On the right side, it grows very quickly up to infinity. All right. So the domain and range can change based on transformations of these parent functions, but just know that for our parent functions, these are going to be the basic domains and ranges. Now, when you're doing domain and range, you want to be sure to remember that the square root function is an outlier with a domain of 0 to infinity. And this is because you can't take the square root of a negative number. However, when you do horizontal translations, you could have a negative value for x that would make the expression under the square root equal 0. And that's the big thing here, right? Anytime you have a restricted domain, there are ways to find what that x value would be, and not just that it's always 0. And that's if you've got, let's say 2x plus 3 under the parentheses, or under the square root. When you're looking for a domain and range on a graph, it's important to notice the end behavior of the graphs. This will tell you which directions the graphs will continue going forever. So let's take a look at a couple examples here. And I put a graph on here just for your own purposes. I'm going to look at this graph on here. So let's graph the function 1/2 x plus 2. And then we'll close that parentheses, we'll square it, and let's take a look at the graph here. And so we can see from this graph, and I'm not going to put my graph on here, but I'm just going to look at it here. The domain, since it's just an x squared function, is all real numbers. That's negative infinity to infinity. And then the range starts down here at 0 and goes up forever, right? So that would touch 0 and then go up forever. The fact that we have a 1/2 and a plus 2 in there doesn't really change our domain and range, although it does drastically change the shape of the graph. It looks like I forgot to change this example, but let's do this. Let's add a plus 2 on the end. So if I add a plus 2 on the end of this function, we'll see it has the same overall shape, but this point we know has been shifted up 2 units. If we look at the table on our graphing calculator, we see a negative 6, 10, 6 or negative 5, 6.5, negative 4, 4. Our y values go down until we get to negative 2, and it bottoms out at 2, and then it starts going up again. That's a good indication to me that 2 is our lowest y value. So the domain, again, there's nothing that we can restrict, nothing that restricts the x values that we can put into this. So that'd be negative infinity to infinity. And then the range, our lowest value that we touch is 2. So let's put a bracket around 2. And we see that both ends of that graph continue to go up to infinity. Okay, let's look at example number 3 now. Example number 3 is x plus 4 under the square root minus 3. So we'll clear out y1. We'll go ahead and graph this x plus 4 minus 3. We'll do a second square root. X plus 4. And then we'll have a minus 3 at the end. So let's look at our graph. And so this point here is at negative 4, negative 3. Now the domain actually starts at negative 4. And it goes to infinity, so the x value starts at negative 4 and runs to infinity. The y value starts at negative 3 and it goes up forever. And then this last example I have for you is the absolute value. To get to absolute value, you'll click math, number, and then the abs. So the absolute value of x minus 5, whoops, I've got a 2/5 up front. 2 over 5. Now let's do the absolute value, math, number, abs. We'll put the x minus 5 in parentheses and get out of that, and then plus 6. All right, we got a really skinny look, or really short and squat looking absolute value graph. That would be at the point 1, 2, 3, 4, 5. So our vertex there is at 5, 6. So our domain, even though our vertex is moved, our domain, we see this going to the left forever and to the right forever. So the domain is negative infinity to infinity. And then the range, the lowest value we get to on the y scale is 6, and it goes up forever. So that'd be 6 to infinity. I'm going to go ahead and pause the video here. You've got 2 more examples that you can look at on this page down here at the bottom. Why don't you try and do those on your own? Ask me if you have any questions, and then you have a little bit of practice on this backside. Now, these are already graphed for you, and I'll talk to you about number 1 before I just let you loose. Notice this has individual points on it, okay? Now, if you've got something with just individual points, know that this is not a function. This is just a collection of points. So we can write this as a curly brace, and we can just write our x values in here, right? So this has an x coordinate of negative 3. This has an x coordinate of negative 2. And these both have x coordinates of 1. So we can just write them as negative 3, 2, and 1. So if you have just disjointed points, you can write them in curly brackets. And notice I don't need to write 1 twice. I can just write it once. And then for the range, our ranges are y values. And we always write from low to high. So our y values are at negative 4, negative 2, 3. So that y value is at 3. And this point, its y value is at 5. You're thinking, like, isn't that a problem that they don't match? One of them only has 3 and one only has 4. No, because we've used this 1 to map to the negative 2 and the 3. So we've used it for 2 different y values, and that's perfectly fine. This isn't a function, but it's worth looking at. I believe the rest of them you should be okay with. If you do have just a couple points on one of them, you can do that, and everything will be okay. Thanks for watching this video. If you have questions, please let me know. I'd be happy to help you out with them.